Hey everyone, thanks for tuning in. Here's my Sonic project, and this video will basically be showing you how it was made and just how the mechanic works and the process that went into making this video. Before we start, I just wanted to mention that all the state transitions from one thing to another are handled by either input or collision. So for example, here in the rail, this is handled by collision, and boost is handled by inputs, like that. For the regular movement, it basically is divided into 4 different sections, which is getting the movement direction, calculating the max speed, adding a vertical velocity component, and applying it to the rigid body. Those are the 4 different steps. As I mentioned before, the first step is movement direction, and on the right in the inspector you can see that as I move the camera, the object rotates, and it's basically I use this object that rotates based on the vector between the player and the camera angle, which gives me a camera relative direction. So that's how I use that to get the movement direction relative to the camera direction. Then to get it according to the surface the player is on, I grab the normal of the surface, which we see as this blue ray, and then I grab the movement direction, which is the red ray, and I project the movement direction onto the normal of the surface, giving us the surface applied direction, which is the yellow ray. Here, if I slow down time a little bit, you can see it in action. And as you can see, the yellow ray is based on the surface, and it changes as the surface changes. And that's basically how that portion is calculated. For the second step, which is calculating speed, we rotate our current velocity towards our max speed. And our max speed is determined by what surface we're on, and the surface types are flat, going uphill, and going downhill. And that's how that is determined. So I can go to this scene and make it a little easier for everyone to see. As we can see at the bottom left, those are the stats and of everything currently. The max speed for a flat surface is 150. The max speed for going uphill is 115, and the max speed for going downhill is 210. And the way that's determined is by calculating the angles of the normal and a vector up. So let me show you. The blue ray is the normal of the surface, and we compare the normal of the surface to just an upward vector, and we grab that angle. If the angle is 0, so here, then we're in a flat surface because there is no difference. But if we're in a slope, then the angle won't be 0, as we can see there. Now all that's left to determine is basically if we're going uphill or downhill, and we can see that by the y velocity. So if the angle is not 0 and we're going upward, and our y velocity is going up, then that means that we're going uphill, as we can see down below in the debug log statements. And if our angle is not 0 and our y velocity is going down, then that means we're going downhill, and that's how that's determined. And if we go back to the forest, we can see how this moves around in a more dynamic terrain. And that's how we calculate the speed. As for our third step, we add a vertical velocity component. And so what it basically is that when we're in the ground, now as we see below in the console window, we don't have any sort of vertical velocity factor, but when we're in the air, we apply one. So we simply get the y velocity that we have when we're in the air, and we just simply start lowering it to simulate gravity. I'll jump from a higher point to make it a little easier to see that's diminishing. And yeah, so we just grab that and do that. And after that, we have our horizontal velocity and our vertical velocity. We simply apply it to the rigid body, and that's how the movement happens. And yeah. Now for the rail grinding, I used a dolly cart and spline to create the actual rails. So these blue lines, they're the actual spline, and that's how I actually just make the shape of the rail itself. If we zoom in on this rail per se, let's just zoom out a little bit. It has a dolly cart inside of it. So if you just want to modify the rail, you can, not that, you can just go to the rail, we go to the dolly spline, and we just modify it in whatever way we want. I'll just leave it back to how it was for demonstration purposes. And yeah, so that's how the actual rail was made. As for what happens on start, I procedurally generate colliders around it. You could use something like instantiate object, but I just decided to generate colliders. So that's kind of what I went through with. So here, if we go to the procedural rail, this one, the one we clicked on, we can see those colliders around it. And so the way the movement works is like so. If we click on the gizmos and we expand this and go up to here, once we land on the rail, when the rail actually detects the player, as you can see, the dolly cart itself, that red bar was the dolly cart. The dolly cart itself calculates and moves towards the player's position, and from there we move the dolly cart and we make Sonic follow the dolly cart to give the illusion that we're rail grinding. So in action, the way it works is like this. Let's just speed up a bit and slow down time. As you saw, the dolly cart moves first, and the dolly cart moves first, and then Sonic follows the dolly cart, giving it the illusion that Sonic is rail grinding, when in reality they're just following the dolly cart. So yeah, that's how that happens. As for the actual speed that the dolly cart goes in, it's the speed that the dolly cart starts in is the vector dot product between the tangent of the spot that the player landed in and the velocity of the player itself. And that's how we calculate the speed of the actual dolly cart. And that actually works really well, because for example, if you enter the rail like this from around this angle with a lot of speed, let's just do more. We get around that much speed, but if we enter from this side, from a little better angle, we get even more speed. So with that dot product calculation, we're actually able to preserve the momentum that we had going into the spline. So that's how the actual rail grinding works. So to give it a conclusion, basically player lands on spline, and the dolly cart moves towards wherever the player is, and then the dolly cart moves with speed based on the dot product between the tangent of the dolly cart, the tangent that the dolly cart is in after it was placed towards Sonic, and the velocity of the player when they enter the dolly cart. That's how we move the dolly cart. And in order to move the player, we just simply make the player follow the dolly cart, and that's how the rail grinding happens. The boost itself can also be used in the rail grinding, as we saw, and we can transition into the rails, or spline if you want to call it, from spin dash. So yeah, that's how that happens. The next level design tool is the loop-de-loops. There's two types of loop-de-loops. We have one with camera change, which will be this one, and we have one without camera change, which will be this one. And the way they both work is like so. And let's just turn on the gizmos, and first I'll explain the one without camera change, which is this one. As you can see here, we have a dolly cart with the tangent that represents with a ray that represents the tangent of the position of the dolly cart. And the way it works is like this: when the player is on the loop, this cart follows the player. So the way this loop-de-loop was made is with the spline and dolly cart, kind of like the rail grinding. And so this is how it works. Once the player lands on the rail, the cart transfers towards wherever Sonic was. And from there, it starts moving forward. The difference being this and the rail grinding is this: that based on the camera angle, we get the tangent of the cart's position on the spline. So if we rotate the camera like this, now the tangent is the opposite side. And that's how we were able to get the movement direction. So this gives us the forward direction for the loop. In other words, the path that we want to take. After that, we just simply make the player's orientation forward for the player to match the tangent. So here, if I click forward, that's the result of that interaction. And here, if I click backward, that's the result of this interaction. Notice how the ray at a certain point of the loop, so here, and a little upward as well, so around there, the ray is red. And the reason for that is because note that we do not invert the tangents. We do not invert the tangent's direction during those positions. The reason for this is because once the player has rotated a certain amount throughout the loop will face a different direction in terms of the tangent relative to the camera. So if we go here, now before it was facing forward relative to the camera, here it's facing upward relative to the camera. If we do not constrain and disable the tangents change from camera movement during this section, then what will happen is this loop-de-loop around here, the tangent will change because the camera angle is now facing a little downwards in response to the dolly cart rather than it was at the beginning. So we just simply don't affect the tangent of the dolly cart during these angles, only during the beginning angles. And I just use green and red ray to represent when those changes happen. And that's how we're able to move forward, backwards, right, and left in a loop-de-loop. Now to explain the loop-de-loop with camera angle switching. This one is the same thing as the other loop-de-loop, but the main difference being is that on top of this loop-de-loop's dolly cart and spline, it also has a camera cart and spline, which is that blue line right there. So the way that works is like this: this dolly cart in the loop-de-loop matches the one for the camera spline. So if we look over here in the scene view and we go over here and we click on this dolly cart, we notice that it's on position 0.134, and we click on the dolly cart spline for that, it's also 0.134. So the dolly cart's position for the camera spline matches that of the position that the loop-de-loop dolly cart is in, which matches the position Sonic is in. So that's how we're able to get this sort of camera movement. However, while this works when moving backwards, I do have a toggle here that says only forward direction. So what that means is basically that Sonic can only move in the forward direction of the loop-de-loop. So here, if we go backward, we can move backward, but what that basically means is that if you enter the loop-de-loop from up there, from this direction, and we move that way, then it won't function the same way. And usually this is fine because in Sonic games, these sort of cinematic actions are specifically for that cinematic purposes. So you won't be going back towards these loop-de-loops, which is kind of what we actually see in the Sonic games. So as a demonstration, we can just try that out right now. And just jump here to be able to give us a bit of an impulse. We'll try that one more time. So if I try to go, so here I'm pressing forward, even though I entered from over here, it will still assume that I entered from the opposite endpoint. And so that's how that works. This is actually fine because when you use these sort of cinematic camera angle changes, then the loop-de-loop you'll usually not go back to it. You can actually check that in Sonic Adventure 2, Sonic Adventure 1. This is how those sort of loop-de-loops actually function. And for developers' ease, I actually made these loop-de-loops without a camera to be able to have that option just in case they want, that ease of action, but they don't particularly need to put it. But if they've toggled it on, then here, notice how the tangent doesn't change no matter what direction the camera is facing. So yeah, that's how those loop-de-loops happen. As for how to modify the loop-de-loops, if we go here back in the scene, again, the loop-de-loops were made thanks to spline and dolly cart. So here is the dolly spline. If we move something upward, it'll just adjust it to whatever I want it to be, and that's how that is made. Uh, and yeah, I usually use the Cinemachine Spline Smoother to be able to smooth it out once I give it a normal outline of this sort of loop-de-loop. But yeah, that's how that is made. For the homing attack, what we do is we first check for targets inside a radius around the player. That would be this radius that yellow sphere that we see. And after that, we filter targets um, from those that we collected within this sphere. When we press homing attack, we filter them out based on if they're in the camera view, and if they are, we assign them a score based on how close they are to the center of the camera and how close they are to Sonic himself. And whichever has the best score based on those two factors will be the homing attack target. So let's just see it in action. And that's how that works. As we can see here below, let me just clear the log to show it a bit more clearly. If we do it just once to display it, here we see that the colliders gathered were a few enemies, and from those enemies we saw which ones were the potential targets. Notice how this enemy one was no longer accounted for because it was not within the camera view. And however, because we do have potential homing attack targets, we will hit at least one of those targets. So that's what happens when we have something in view. What happens when we don't have something in view? So or in view or if we didn't gather collider, we simply apply an impulse forwards. Now let's see what happens when we get close. So now we're close, but we're not within the camera view. Then we simply apply an impulse forwards. Even though we did collect enemies around the sphere, none of them was within the camera view, so none of them are considered homing attack targets. Now to display the momentum as well as how it would look in a bit more of a sandbox scene, I will show you like so. Go down here to where it says homing attack. So here's the homing attack impulse after attack momentum. And so the way it works is once we reach an enemy, we simply set the velocity upward toward. We simply make the velocity upward for Sonic, kind of giving the illusion that he's bouncing off, and then we project that. Onto the horizontal velocity of the player. And so right now, how impactful the horizontal velocity is by this scaling factor. So if we make it something like 0, then the horizontal momentum will have no impact. So if we do something like this, I'm holding forward, but it doesn't go that far. It goes just straight up. But if we do something like 4, which is much larger than what I had before, let's see how that goes. It's a lot more impactful and a lot stronger. So it creates this really quick and fast-paced traversal. And what's really helpful about that is that we can set different objects to different momentum impulses. So which would give the illusion of different types of bouncing off of homing attack targets. So yeah, that's how that works. Thank you so much for watching. I hope that you liked the video, and I hope you're able to make some really awesome Sonic games with this build.